Hi, everybody. My name is Chris Mitchell. I'm one of the regional managers for Red Valve Company. Today, we're going to talk about Tideflex check valves.
I'm also with you, everybody. It's Mike Dewar. I'm the chief engineer of Red Valve. If you've been in these presentations, you had three so far. Similar concept. We sort of have a sales and engineering presence in both. Mr. Mitchell here has been with this company about 40 years or so. And so he's going to be the master of this presentation. I'm going to be the color man, if you will, similar to the other presentations. But you'll get sick of me tomorrow if you're attending because I'm doing all three of them. So glad you guys are with us. Just like the other ones, for any of you, if this is a new presentation you're attending, there's that Q&A box. So just as this is going on, you can type any questions. At the end of them, we'll start going through those and answering those questions. So glad to have everybody.
Okay, off we go. So I want to start us off today with the major issue that led to the development of Tideflex check valves. And this will help us define our terms a little bit and give you an idea of where this whole product line came from. What you're looking at here is a very, very basic schematic of a combined sewer system. Essentially what we have is we have businesses, commercial buildings, homes, recreational facilities, all kinds of infrastructure sharing the same sewer system. What's important to us is this unprotected outfall here to the right. Basically what happens, in this particular case, we're showing you the ocean. So let's say the tide goes up, the water rushes in to the sewer system, it eats up its capacity to store a rain event. At the same time, all these businesses and homes, they're flushing toilets, using dishwashers, all of that gray water and sewage, if you will, comes into a sewage system that's already full. So what happened over time as cities started to grow, the sewer infrastructure did not grow with them. So what the cities did was they created these, or allowed for these regulators to be built. When this sewer is already full and everybody starts to use it, they allow raw sewage untreated that the plant can't handle to fall out into the waterways of the United States. That can be a river, a stream, the sea, a pond, a lake. And as you can imagine, it creates all kinds of problems for pollution. So those are unprotected outfalls. So this is a huge, huge infrastructure problem for cities all over the country, and in fact, all over the world. So the first use of a Tideflex check valve was placed on the end of these outfall pipes. So now, in any kind of event where this tailwater rises and would have normally filled the sewer with water that doesn't need to be there, the Tideflex valve keeps it out. It does a couple of things. The major issue being it keeps that storm water sewer system dry and allows it to store a wet weather event. So part of what a stormwater sewer system or sewer system in general is supposed to do is be able to store a wet weather event. If it's full already, it creates all kinds of havoc. Basements get flooded, airport runways aren't usable anymore. If you are discharging to a beach, you've got sewage spills on a beach. In a place like Pittsburgh, if this happens to us, a quarter inch of rain might be cause for a boil water emergency. All of that sewage that goes into these waterways of the United States are usually upstream of somebody's water intake. So that's not a good thing either. So the whole idea and where we started was protecting these outfalls in combined sewer overflow systems. Now, that was a little easy looking schematic there. This one gives you a little bit better idea of what's going on. So not only do you have homes and developments pushing sanitary and gray water into the sewer system, you have industrial plants, may have chemical refineries. You've got all kinds of infrastructure, restaurants, pushing all of this into a wastewater treatment plant. If all of these point outfalls get inundated with water, they will not be able to store wet weather events and sewer spills occur. So that's where these combined sewer overflows occur. So combined sewer overflow is not only, just to go back to this, it's not only this regulator. So this would be a combined sewer overflow if everything lined up to send water out of this pipe, but it's also an event. So it's what happens when sewer systems get inundated in combined systems and dump out into waterways. One of the things that the EPA, with whom we were working on the development of this valve, identified as one of the main culprits to why pipe systems, sewer systems get inundated with water that shouldn't be there is flap gates. Flap gates have been around for hundreds of years. Typically what they are is some sort of frame, some kind of plate attached with some kind of hinge mechanism. The frames, as you can see in this photo, are in pretty good shape. The plates are in excellent shape. The problem is the hinges. Hinge pins rust, they corrode, they require a lot of maintenance. In some cases, they require lubrication. Flap gates tend to be heavy. They tend to have a high cracking pressure. They might have trouble discharging low flows. Flap gates are made out of all kinds of materials. These are steel, they're cast, they're aluminum, they're plastic, all kinds of materials that companies have tried over the years to try to mitigate these inflow issues caused by flap gates.
Hey, Chris, can you go back one slide, just real quick here? One more. And just to get everybody in the ballpark, as Chris and I were talking about this, realize, and Desert reps, maybe some or all of your businesses inside the plant, we want to introduce outfall pipes first. Like, what are these things, these outfall pipes? And as Chris mentioned, that's where it started with those CSOs, those combined sewers. He'll get into that a little more. That's what drove the development of the Tideflex, but the whole other section is stormwater, right? That can be completely separated from sewer systems, what have you. Those have outfall pipes too. That's when you look down in the street and see the grates, right? That's all collecting stormwater. That's going to go to a natural water body. Eventually, it's going to discharge the river, ocean, what have you. So there's CSO and there's stormwater systems. And those outfall pipes are just what the name says. They discharge that flow into some natural, water body. Just
correct. And that's a good point. Thanks for that. And so the whole upshot of this thing is trying to keep all that receiving water, all this river water, ocean, creek, pond, lake, whatever it is, out of these sewer systems so they can store a wet weather event. One thing I didn't mention, let's say this is an ocean, and during a high tide, maybe a king tide, hard wet weather event, it inundates that sewer system and gets back to the plant. Now that plant's cleaning salt water, which it really doesn't need to be doing. That salt water can get into the process and just cause a lot of disruption, and again, a lot of cost to infrastructure. So again, another set of flap gates. These are in really good shape. I mean, you look at them, there's not a whole lot wrong with them. The hinges are the problem. The valves don't close all the way. They don't open when they need to. In this particular town, they had to make a choice. You want the valves open to allow drainage? Are you going to let a little backflow in once in a while? They chose to prop the valves open and allow the stormwater upstream to drain. This is a really, really old flap gate. This is a timber gate. These are wooden boards held together with a metal frame against the brick wall. And again, I mean, we've got warpage, we've got corroded hinges. This is just typical of flap gate valves and the issues that come along with them. They either don't open, they don't close properly, and if they don't close correctly, they allow flow to inundate a sewer system. This is San Francisco's airport. These are 2 of the 4 pipes discharging from a stormwater detention basin under one of the runways. This is a pump system. You can see that these flap gates are not closed. If this bay rises during a wet weather event and fills up these pipes, filling up the detention basin, and the pumps can't handle the flow fast enough, what you end up here is water on the runways, and you could theoretically close down that particular runway. The answer to this is one of the very early applications, was to apply Tideflex check valves to these pipes. These valves are still there. So what was going on back in the early 80s, mid 80s, is the EPA commissioned red valve to test and develop an alternative to flap gates. The EPA had determined that besides some of the other infrastructure issues that caused I&I, broken pipes, and all the other things that can happen, tide gates, flap gates, if you will, were one of the biggest culprits that resulted in these combined sewer overflows and the inundation of sewer systems. So they came out with a document that was a development and evaluation of a rubber duckbill. And what their goal was increase the reliability and performance of tide gates in order to get a beneficial impact on the general pollution abatement program for the nation's waterways. Real long story short, they're trying to quit dumping sewage into river streams in the ocean. That was really what their major goal was, having identified the problems associated with tide gates. We went into a 2-year testing program, at the conclusion of which the EPA came out with a statement that turned out to be huge for us. They stated that the results of the project indicate that the rubber tide gate can provide low maintenance, reliable performance as a cost-effective alternative to conventional tide gates. They wrote a document, combined sewer overflow manual, in which they showed these first Tideflex valves, and from there our sales and production of this product went vertical, because now it was an endorsement of the technology for use on these combined sewer overflows. So that's kind of the beginning of this whole project that we call the Tideflex. We, since 1984, have been continuously testing. We're constantly developing the product, looking to improve its performance. The first check valve we sold is the one you see in this photo on the right. And now this is a little bit dated comment. There are many millions of Tideflex valves out there in all manner of backflow protection applications. So what's a Tideflex do that a flap gate doesn't do? Well, number one, we're 100% elastomer construction. If you went and looked at the presentation on pinch sleeves, maybe yesterday, we're built kind of the same way. Raw rubber impregnated fabric, hand laid up, 100% elastomer construction, no links, no levers, no moving mechanical parts. It operates on differential pressure. When the valve is in a passive position, it's closed. When it sees flow, it opens, and any amount of reverse differential keeps that valve closed. There is no maintenance to do on these valves per se. We recommend a periodic inspection. You can get things like 2x4s, shopping carts, all kinds of debris get caught in them. What we recommend is those be removed, and off we go. The valves have a very low cracking pressure, generally between 1 inch and 3 inches of water. They are self-draining, which is really important, especially when you start to get into coastal areas like Florida, Louisiana, Mississippi, where mosquitoes are a problem. The valves have very low head loss. Because they're flow operated, they're quiet, they're silent and non-slamming. There isn't a spring that's going to take over and cause that valve to slam. Installation is relatively simple, although some of the applications we deal with can be rather complex on installation. We'll look at some of those. These are custom built for specific flow and pressure conditions. We build these valves by hand. So as we're building them to meet flow rate requirements, pressure conditions. We don't manufacture a one size fits all Tideflex valve. We've continuously been doing extensive independent hydraulic testing, generally at Utah State Flow Laboratory. And our R&D is continuous. It just never ends. So manufacturing is very much like pinch sleeves. So here's a mandrel. It's just sitting on the station. It starts to get wrapped as we get finished with the number of layers we need to get the valve to where we want it. It gets wrapped with a tape, put in a vulcanizer, cured, and what comes out is the finished product. Now, hand fabrication. There's a lot of art to that. So to give you an example, why do we do that? Well, if we needed a mold for these large diameter valves, those molds could get into the hundreds of thousands of dollars. We would only be able to build one part per mold, and it would be very difficult for us to maintain any kind of production. Hand fabrication allows us to build the right valve for the application and customize it in order to meet the various pipes upon which they need to be applied. This is 20-inch. These are all the valves we build for 20-inch pipes. So we've got 20-inch pipes that come in at 19.9. We have them at 21.9. We get them at 530 millimeters, 23.5 inches built on a 20. All these sizes are built on one 20-inch piece of tooling. That's what the hand fabrication process allows us to do. We can build it on steel pipe, corrugated metal pipe, both spiral wound and concentric, HDPE, steel, concrete, you name it, we can build a Tideflex valve to fit over the OD. So the first valve that we manufactured was called a TF2. This is the valve. It's you'll see that it flares from center line, both top and bottom. And again, 100% elastomer construction. Don't worry about rust and corrosion. Will not warp or freeze, open or shut. Custom built, low cracking pressure, 1 to 3 inches of water, low head loss. Now, the materials of construction are the same materials that we use for pinch sleeves. Neoprene, Hypalon, Buna-N, EPDM, Viton. We do manufacture Tideflex valves very specifically for TMS applications. Mike will talk to you about those in another session. For drinking water reservoirs, mounting clamps, stainless steel, Monel, Inconel, 2507. I mean, it just, anything that we can buy in flat, we can make a mounting clamp out of. So all these different materials, all these different configurations are all built off one piece of tooling, allows us a lot of flexibility to meet pipe ODs.
Chris, I just got a couple comments before you go. Just once again, back when you look at flap gates, and I'm sure you're familiar with people that don't maintain their equipment, even inside of a plant, right? They don't do it at the necessarily the frequency they could. If you imagine an outfall pipe, and you saw that one sticking in weeds and mud and all that, nobody goes and maintains outfall pipes. So, and the connection I'm trying to make is, if you got a nice pristine plant, they may not do the inspections of valves, what have you, and that you can imagine nobody's going to go pay attention to an outfall pipe. So even those flap gates only have 2 hinges. There's not that many mechanical parts to it. It's 2 hinge pins. Nobody pays attention to them. That's why you see, they're corroded open, shut, frozen, the whole bit. That's the reason where the Tideflex that operates on differential pressure, it doesn't need any maintenance. It's really periodic inspection. That's why it was such a huge benefit. I mean, the flap gates don't perform well to begin with, but nobody maintains them. Nobody greases them. Nobody replaces parts. They're ignored. if you can imagine that. That's why there was a big driver for that. Plus, obviously, they're ineffective at preventing backflow. The second thing, just to talk about the construction just a little more, even if we could make molds for these, the fabric reinforcement is what is key as far as the hydraulics and the back pressure rating. We don't make one size fits all. We have different back pressure ratings of these, which is a different construction. It is very similar. If you ever watched a truck tire be built, it's very, very similar in that process. So we also have within the wall thickness, different, say, durometer, different mechanical properties of elastomers and fabrics that are within the wall thickness. One of the biggest challenges we have with this valve is it looks simple, right? It's black and it looks like a duckbill. The magic is what's inside the wall thickness. You don't build that thing right, that tide comes up or the river comes up 5 feet, that thing will turn inside out. It'll actually invert is what we call it. So that hand layup is, as Chris mentioned, is not key to, so we can build so many different constructions. It's absolutely necessary. If we just molded that out of just molded rubber, it wouldn't have much of a back pressure rating whatsoever. Okay, there's just a couple comments.
Yeah,
Thanks.
and we're going to look at some curves in a little bit. And this, you'll see where Mike talked about reverse differential inverting valves. You know, the valve is simple, but how we manufacture it, the criteria for manufacturing can be complex. This is just simply a TF2 data sheet. We've got these data sheets all over our website for all the different products. I just wanted to point out that that's all available. So to give you an example, here's that TF2 that we came up with in 1984. All of these products that you see on this page are offshoots of that valve. I'll get into these in a little deeper dive on some of them, but to give you an example, the TF2 flares from the center line, top and bottom, great valve. But we do have some applications where the pipes are very close to the ground, whether it's in a structure, a seabed, a riverbed. We had to come up with a flat bottom valve. Slip-on valves. I don't like slip-on. I need a flange. Okay, we'll give you that. Some applications, we sell to big box stores, Walmart's, Kmart's, Walgreens. They're landlocked. They don't have an outfall pipe. They've got to handle stormwater mitigation on site. So they need inline check valves to put in their manholes to keep reverse flow from coming back and getting them. And then inline check valves for process type applications. The Checkmate, we're going to talk to you about that tomorrow. And then some process applications that arose just because we had a way to either increase jet velocity while we're preventing backflow. So we'll get into these a little deeper. All these mechanical devices you see here were developed in order to allow us to install these check valves, these Tideflex valves, in places where they don't necessarily have a stub of pipe upon which to put a slip-on valve. And we'll take a look at some of those as well. So the mounting styles for Tideflex valves are relatively simple. We do a slip-on type valve. The cuff portion of that valve, the inlet side, is sized to fit over the end of the pipe. It gets clamped onto the outside of the pipe. We also manufacture valves that are flanged to the end of the pipes. This is a client preference in a lot of cases. They just prefer a flange connection to their outfall pipe. This one is on the Mississippi River, this flange valve. There's a little bit of traffic down there. They feel a lot more comfortable if that valve is flanged to that pipe. It protects their investment a little better. Slip-in valves go inside structures. And of course, inline valves are primarily used for process type applications. So for about the last 36, 37 years, we've been doing all kinds of testing. We have done CFD modeling. We have done flow testing. This photo down here is Utah State's Flume. I believe they can do up to about a 60-inch valve. This is some of the performance and pressure testing that we did at Utah State. computational fluid dynamic for mixing water reservoirs. I'm just going to go over this stuff very briefly. What all this stuff does is allows us to manufacture valves of different configurations, like Mike said, different stiffnesses to allow for greater flow capacities and lower head losses, allows us a lot of flexibility in the product that we're trying to present to the market. We are primarily concerned with moving water as fast as we can at very low head loss. That's the game. So with that in mind, to give you an example, these are head loss curves of the three basic type products that we manufacture. So this is a 24-inch Tideflex inline check valve. This would be the valve that's shaped like a wedge. These curves that you see we call them back pressure curves. These relate to the stiffness of the valve. These are maybe a little hard for you to see. The low curve is 2.5 PSI. The high curve is 20 PSI. That's the pressure the valves have to withstand coming at them, assuming an empty pipe, right? So 37 Gs are inline valves. But you pay a little bit of a penalty for some of these. A 10,000 gallon a minute flow at 10 PSI back pressure, that's this curve, is roughly a 17-foot head loss. That's relatively high. Doesn't mean the owner can't stand it or the engineer. It's just a relatively high head loss. Just by changing that valve to an end of pipe type or inline type Tideflex, that same 10,000 gallons at 10 PSI back pressure gets us to about a 3.5-foot head loss. Then again, you can add a checkmate into the mix. I'm not going to steal Mike's thunder for tomorrow, but that same 10,000 gallons a minute at 10 PSI back pressure is a 1.30 foot head loss. So what we're trying to do is always provide the right valve hydraulically to meet the application. We're trying not to create the problem we're trying to avoid. Too much head loss at the end of a pipe creates flooding upstream. It's what we're trying to avoid all the time. So principle of operation is very simple. Differential pressure, 1 to 3 inches of water cracks the valve and allows flow. At rest, the valve is closed, and any amount of back pressure over line pressure keeps the valve closed tighter. What we need to know to manufacture a Tideflex valve is relatively simple. If it's a slip-on TF1, TF2, we need to know the pipe OD, right? We need to know the outside diameter of the pipe. If it's an inline check valve, whether it's a series 37, 37G or checkmate, we need to know the ID of the valve or pipe. And if it's flanged, of course, we need to know the flange drilling. Generally in the United States, it's 125-pound ANSI, but in different parts of the country, we do all kinds of drillings. Australia standard, South Africa, PN10, PN16, all kinds of drillings, JIS. And the other thing we need to know, if the valve is going to have a curved bill installed, what direction the current is. Now, the biggest thing probably we need to know is right here, back pressure. Back pressure to us, assuming an empty pipe, is measured from the invert of the valve to flood level. If this is 10 feet, it's a 10-foot back pressure. This tells us how stiff we need to make that valve in order to withstand that back pressure. If we build it too light, like Mike said, the valve might invert. And that's what we're trying to avoid. And all those different curves you saw on those charts, different pressures relate to stiffness, right? So you could have a valve that's 5 feet submerged. You could have it 10 feet, 20 feet, 30 feet, 100 feet. We need to know that. So these are the three things we need to know before we can even manufacture the valve. In fact, we won't manufacture it without it. So a lot of people don't ever get to see these valves operate. So probably not to a lot of our clients is how they close. And then becomes watertight.
Hey, Chris.
Yeah, jump off that slide, Chris, because that the actual audio sort of muted the audio of the videos muted your audio.
Oh, okay. Thanks for letting me know that.
Yeah, they just
So at any rate,
ran it.
just to back that up without, well, we can look at them still. So basically, when we were looking at this valve discharge, the first thing you saw was really, it's a pump discharge. Air was getting blown out of the valve and then flow commenced. You'll notice that the valve never went full round. They generally do not. They kind of open like a soft diamond. And that shape of that opening and cross-sectional area is taken into account when we calculate head loss. As far as closing goes, you saw that as flow dissipated, the valve offered a very soft closure, no slam, and closes drop tight. So the parts of a Tideflex valve are generally the cuff, that's the part that slips over the pipe, the saddle in the center, and the bill at the end. So at least we can discuss various little finesse features of the valve, and you'll know what we're talking about. Most of the head loss associated with the valve is built into the saddle. So TF2s are slip-on valves. Up to 12-inch, we supply those valves with band clamps, as you see in the photo to the left. Larger than 12-inch, we use fabricated clamps. You'll notice these holes in the clamps. We recommend the valves are pinned to the pipes. We don't see a whole lot of end thrust on these valves, but it secures the valve. It makes sure that the contractor, should he not tighten those clamps enough, the valve stays in place and doesn't fall off the end of the pipe. It's just a security feature. I show this photo, it shows corrugated HDPE pipe. And again, to remind us that we can put these valves virtually on any type of pipe, provided that we have a bandle large enough to get a valve over the OD to the pipe. Also, you see the valve pinned here. And again, it's a safety feature, make sure the valve stays connected to the pipe. In some of these cases where they're large diameter, it's pretty big investment. And we want to make sure that client hangs on to that valve. One thing about the TF2, back to this one. This is the valve that flares from top and bottom. So the original Tideflex, it needed a lot of space, needed some ground clearance below it in order to get that valve installed. So it did have some limitations for installation, especially if you were in a manhole and you had a pipe close to the floor. You had pipes close to riverbeds, seabeds, creeks, and things like that. We need a lot of bottom clearance in order to get that valve installed. So basically what happens is, to dramatize this a little bit, a 72-inch valve needs a ground clearance of about 32 inches. So you've got the mass of the valve below the invert of the pipe, plus we ask for additional 8 inches. And that's to account for any flex of the valve once it's full of water. It is all rubber, so it's going to move around a little bit. We need 32 inches of clearance. So we're always mindful of where TF2 type valves are going to be installed. Stormwater drainage applications, like Mike said, this is a really big application for us. This is in Boston near Deer Island Treatment Plant. All this is on the other side of this wall is a road. It does get inundated, so they use a lot of check valves. You can see these are series TF2s. The pipes are relatively high off the ground, and therefore they can be installed here. Even this valve that's really low into the riprap, it's clear enough that we can get a TF2 in there without obstructing the valve and allowing it to free flow. Stormwater pump stations, same thing. All these pipes have to be up off the ground enough to where we can use a flared TF2 type valve, but just to give you another type of application where these valves are used. Arroyo Vega in Argentina, these were 13 90-inch TF2s. Again, this was an interesting design. This is a river that's cofferdammed upstream up in here, our businesses. And what was typically happening is the river was consistently backflowing up into the business district, flooding them out. They built basically a wall, allows the stormwater to flow out into the river, but keeps the river outside the business district. These are up off the ground, adequate to allow for the installation of series TF2s. So no sooner than we get that valve, we start to hear about people's problems with those type applications and structures like manholes. The pipes are close to the ground. We just can't get a TF2 installed. So back to the drawing board, and we came up with a design for a flat bottom valve. We called it a TF1. So interestingly, a TF1 came after a TF2. And basically what we did was took the cross-sectional area that used to be down here in a TF2 and we put it up here. Same benefits, features of the TF2, 100% construction, won't rust or corrode, no warping, same materials for the clamps, but a flat bottom valve that facilitates installation in areas where you don't have a lot of bottom clearance. So again, same thing with the TF1. Cuff section fits over the pipe. Saddle section in the center is where it's built for strength to withstand back pressure, and the bill of the valve is what closes the valve tighter. So this is the type application where the TF1 was most demanded. So prior to a TF1, where all we had was a TF2, we actually had clients that would break up the floor of manholes to get a TF2 in to avoid using a flap gate. And of course, that's no good because then you create a sump. So all new tooling, the whole bit. So we made a very significant investment in order to get this TF1 to the point where we could use it in structures in low areas. Now that same 72-inch where we needed all that bottom clearance, right? We needed 32 inches. Now we need 6 inches of ground clearance. So this became a very, very significant improvement over TF2s when it came to installation. So to give you an example, this is a stormwater detention basin in Arizona. If you ever get out there, maybe you're there now, football fields, soccer pitches, a lot of those are below grade. They're there to collect stormwater during wet weather events. They allow stormwater to drain into them rather than sit around on roads and foul up their infrastructure. You would never be able to get a TF2 in there. So what that TF1 did was allow engineers now to start lowering their pipes, take advantage of the slope of the pipes to increase their outfalls. This is a residential drain. This again, another outfall pipe going out into a lake, series TF1. Would be very difficult to install a TF2 here. The curve bill design came somewhat later. Curve bills allow us to build a very, very much more flexible valve. What the curve bill does is it increases the sealing area of the valve. It actually increases the length of the bill. Essentially, what happens is when flow hits this curve bill, the flow opens. When flow dissipates, it curls back up. And when back pressure hits it, flow coming this way, it closes tighter. It retains the same dimensions as a straight bill. It does not increase the head loss any, but it offers a greater sealing area to the valve in a closed position. And it's got the ability to close a little better because it's such a light construction on stones and silt and debris like that. So that was the next improvement. So this is what that curved bill looks like on a production level valve. Now, one little thing about this valve, we talked about this earlier, where the valve flows at about 1 to 3 inches of water. So here's a little bit about hydraulics. When we see this flow exiting this valve, and we know it takes about 1 to 3 inches of water over back pressure to flow, we know that water level's somewhere right about in here. So as this tailwater starts to rise, the water inside the valve starts to rise as well and still flows over the top. That is very difficult to get in a flap gate. So pinning and bolting, again, we recommend that. To be honest with you, contractors do and they don't. We tend to include that in our specifications, point that out to the owner and the engineer, and ask them to make an integral part of the spec. This device you see at the end of the valve, we call a clevis. This is merely there to assist in lifting the valve, right? So for installation. So you can strap the valve at the cuff, grab it with another strap or a hook at the clevis, bring the valve in, and attach it to the pipe. Pinning bolting recommendations are in our drawings. You will see them here. They're also in our notes. So we put them all over the place. We have some details in our IOM that show a number of different ways to affect the pin. Now, rubber cuff adapters. One thing about a Tideflex slip-on type valve, you can miss big. If you make a mistake and you order a valve too large, what we can build is this section right here. It's rubber and rubber impregnated fabric. Basically, it's like a car tire rubber band, if you will, that gets mounted to the pipe, makes up the difference in size, and then you can slip the Tideflex valve onto that and get the valve installed. If you order the valve too small, then you're going to be out of luck. So this all goes back to the couple things we need to know before we can manufacture a valve. And of course, a slip-on valve, we really need to know an exact pipe OD. So this is what that looks like. So in the case, this actually, I was on this call. This is in Chicago. This is corrugated metal pipe. They missed. They ordered the valve about 2 inches too large. So we built a 1-inch thick band, bolted it to the pipe, attached the valve to that band, clamped it up, and off we went. So there are ways to mitigate some of these problems with mistakes. We also manufacture flanged end valves, both flared and flat bottom. The Series 35 is essentially a TF2 with a flange. The 35-1 is the TF1 with a flange. Some clients just feel a lot better about mounting Tideflex valves to the wall. They just have a much more secure feeling about it. So you can mount directly to head walls. You can mount to mating flanges as well. There's a direct wall mount. This is a direct wall mount. We supply the rings. The rings are typically galvanized steel, stainless steel. Generally speaking, we don't supply 304 anymore. The cost between 304 and 316 is so close that we are just, we've gone to 316, although we will supply galvanized steel when requested.
Just as a quick thing here, and we get asked all this time. By default, we put an ANSI drilling in that flange, just like the rest of our valves. Most of these outfall applications don't have a whole lot of differential pressure. It is possible when you get asked the question, we stick with the standard. There's the ANSI drilling. You put J bolts, you put anchors, you put drop-ins, what have you, in the wall. It is possible that they could use fewer bolts. So if that's one of the questions you get, just as a heads up, are we going to be able to use fewer bolts? That's when you can contact us, and that's going to be a possibility. There's sometimes we can use, half the bolts, depending on the application and pressures. Really what the limiting factor now is the space between two adjacent studs providing enough compression on the rubber flange to provide a seal. It really has nothing to do. The thrust forces are nothing compared to how much those anchors can withstand. So just to keep it back in your mind, if you get that question, somebody wants a flange valve, they come back to you and want a fewer number of bolts. Can we use fewer, smaller, what have you? That's a possibility.
Yeah, I mean, at the end of the day, all we're trying to do is make a water stop. because like Mike said, we don't see a whole lot of end thrust on these. So this is I'm going to show you this animation. This is something you can use with your clients. A lot of times we just use this for sales presentations, but it's kind of the way we're going. These were actually made by our office in Latin America, but it gives you kind of a nice idea of how the valve sets up, what it looks like, how it operates. I'm going to stop this right here for a second because in a couple minutes, we're going to talk about these mounting plates. You notice this valve is on a mounting plate. Keep in mind, we have a head wall here, but there's always a pipe going through that head wall. So just keep that in mind as we go through and we talk about my mounting plates coming up. Different layers of material, different layers of raw rubber, different layers of fabric. That's where we get the strength. That was that saddle portion of the valve that gets built up to be able to withstand back pressure. So you're kind of getting the idea. There's a TF2 with a flange of 35. Everything's an offshoot of that original series TF2. So mounting plates. This is Huntington Beach, California. So why do we use mounting plates? There are a couple reasons. One, in this particular outfall, which is pumped, turns out this head wall was pretty broken up. Originally, well, first of all, there's no pipe stub upon which to put a slip-on valve. Originally, we were looking at flange valves, but the more we looked at the head wall, we were afraid of putting a bolt pattern around those pipes because we were very, very close to the idea of the pipe to the extent that when they started to put bolts in there, we were afraid they'd spoil the pipe. So by putting the valves on a mounting plate, we spread those bolts away from the pipe opening and give us a solid base to put these valves on. So to give you an example, another reason we use mounting plates. So to give you an example, here is the original opening of this culvert box. We don't have one Tideflex valve that can fit over that box. So what we do is we take a look at the flow. We have the engineer give us his best estimate on what the flow rate through this channel would be. We send it back to engineering, to Mike and his guys. He figured out what the flow capacity of the largest valves we could put on there were and at what head loss, and we came out with a couple of 48-inch valves. We had the contractor put this center section in, we mount the plates to the wall and the valves to the plate. So again, it would have been very difficult to use any kind of round flange on there. So these mounting plates just give us another way to get valves installed in situations where we otherwise couldn't with just the valves themselves. We do offset thimble plates, some head walls, revetment walls. The pipes are coming in at angles. So again, we don't have pipe stubs. So what we'll do is we'll build an offset thimble plate, mount the valve there and go. We mount a lot of Tideflex valves inside manholes. The problem in most of them is they don't have a pipe stub upon which we can mount a valve. So we've got to build one. And because manholes are generally round, we build a curved thimble plate that gets mounted to the manhole wall and the valve gets mounted to that stub. We've done these really, really small. In fact, the drawing you see here is for a 6-inch valve. We do really small ones where we need to get these valves installed in manholes. The new generation Checkmate takes care of a lot of that. You'll see about that tomorrow. This one I always throw in here because it's a little wacky, but you take a look at this pipe. This is a view down into the channel. This is actually an arch pipe. You see the floor, it's not quite flat. So it's got a radius there. It comes up, it's got another radius. We didn't have one Tideflex we could install down here. We didn't have any way to install it. So what we ended up doing was building a plate that could accommodate 4 valves, 3 large valves, 1 valve at the invert to pick up incidental flow, and everything gets mounted on there, and the whole thing gets mounted to the wall, and backflow prevented in this particular sewer. So as I said, what we do is when we have these odd sizes, we get back with engineering and we give these to Mike and his guys, and they take a look at that opening. And in this case, 2 42-inch Tideflexes and 130 equaled 1 60-inch valve head loss wise. So everything met the criteria for flow and flow capacity and head loss. And that's how the design was derived. Another use for Tideflex valves. This is one of the only times you'll ever see a Tideflex valve mounted horizontally. This is for hydrostatic pressure relief. So this is for any kind of tank that's in the ground. This is for flow equalization. This allows water in this empty tank, right, to come, groundwater to come into the tank, equalize with the pressure on the outside. It keeps from cracking the floors of the tank, and in some cases can keep that tank from floating out of the ground. When we did the first deep tunnel projects in the TARP system in Chicago, those are what, 30 feet diameter, a couple 100 feet deep. We had these valves studded all up and down there to allow groundwater to come in so as not to damage the concrete. So that's what that's all about. We also apply these in landfills on geomembranes. Now, here's the geomembrane. There's a small pipe stub, the Tideflex valve. This is going to vent methane gas. It's going to vent water to keep that geomembrane from bubbling up and perhaps becoming damaged.
Hey, Chris, can you go back one slide?
Sure.
Just for clarification. So I'm going to tell you this now because you're going to hear it for the rest of the time you're repping red Tideflex. Your default answer when somebody says, can I install the bill, which is the end of the portion of the Tideflex horizontally like this, your default answer is no. Okay. The reason some of these can be installed with the bill horizontal, the smaller valves are inherently stiff enough. When you add a layer of rubber, the rigidity of the valve increases much higher than it will adding a layer of rubber to a 48 or 100-inch valve. So we will tell anybody, if you got an engineer owner, if they want to install a valve with the bill in a horizontal position, it is very rare that we say you can do that for that reason. If you did this with a 48-inch valve, it would gap open, look like an open whale's mouth. I mean, that's what it would look like. So that's just a caution right before you even start selling any of these products. Somebody asks you, can we turn it sideways with the bill horizontal? Your default answer is no, and then you can come to us and inquire. But it's really just valves, and it depends. Like I mentioned before, we can do 50 different stiffnesses of these Tideflex per nominal size by changing geometry in the construction. We can make them so flimsy you can pop them open with your hands, or we can make them so stiff you can run over them with a truck. So it depends on the size, the stiffness, whether you can or can't do this. Your safest response is no, you can't do it. If somebody wants to do it, check with us and we'll look into it for you.
And he's being real nice about that because generally we're going to say no too, but we'll take a look at it. In rare situations, we might go for it. One other thing about putting valves horizontal, if you look at the geometry of a Tideflex, if you turn it horizontal, you have to actually flow uphill to get discharge out of the valve. That's going to increase head loss. It's what we're trying to avoid. Inline valves. Now, the first thing you notice is we don't have any bill. We don't have any flare at the end. This valve fits inside the pipe. Therefore, it's got a much shorter bill, and therefore it will have a much higher head loss. In a lot of cases, way over 4 to 5 to 1 than a standard end of pipe Tideflex valve, because it's going inside the pipe OD, and we're going to lose our cross-sectional discharge area. It's fastened with an internal clamp. We still ask that that gets pinned. Again, not so much for the end thrust, but we don't want that valve, if that clamp loosens up, to cock that valve out of vertical orientation. Again, these are custom built to spec for flow capacity and head loss. You can install these now inside the manhole and where space is restricted. So this valve came up in those applications where the client just didn't have an outfall pipe. He wanted to take stormwater measures on his own property. So basically that valve fits inside the pipe, it gets clamped in, and that's what that valve would look like in a small stormwater catchment. But again, relatively high head loss. But if head loss isn't an issue, this valve certainly is viable. We move a lot of this. Thimble inserts, again, another mechanical device that we had to come up with in order to mount inline check valves. Now, this was on the, I think it's the Grand River, Grand Rapids, Michigan. We were looking at, there were, I think, 20 valves total, both sides of the river. This is a head wall back here. And the first design idea was to just use TF2s on pipe stubs out into the river. And somebody informed us that in the winter, they tend to get ice, big ice flows come down there. And of course, if that were to happen, it would shear the Tideflex valves off. So we had to come up with a way to get these inline Tideflexes in. They didn't want to install them all the way upstream, not too many catchments up there in order to do that. So we had to figure out a way to get the valves in so that we could reach up into this bill and manipulate this clamp. And of course, it was a real simple answer, was to manufacture a can, pre-mount the valve, shove the whole thing into the wall, bolt it up, and off you go. Now, going back to what Mike says, you don't need all the bolt holes, but by default, we use an ANSI bolt pattern. We also flange that valve. Now, you can have a piping system where you can spread a couple flanges, slip this thing in, and now you have an inline Tideflex valve. Some clients prefer to go ahead in these catchments, bolt it to the wall, slipped into the pipe, and off you go. Little inline valves. Now we're getting into a little bit of a different type animal. This is what we call a Series 2633. This is a small molded check valve. Fits inside a valve body, 1/2 inch to 3 inch, typically NPT connections, other drillings available, all kinds of materials for the bodies. All the elastomers that we mentioned earlier are available. These are for small sampling lines, inline, small diameter process lines where you need a non-corrosive, non-slam check valve. Series 39s and 39Fs. If you look at this looks pretty much like our Series 35, and that's pretty much what it is. It's built the same way, but this time we're going to put it in a valve body. And again, positive pressure, 1 to 3 inches of water cracks the valve, reverse differential, closes the valve tighter. This is a valve that we use to replace weight and lever, spring and lever valves. Through 24 inch, that valve comes with a cast iron body, large clean out at the top in order to get rid of any solids that might accumulate. Down here at this boss, there are a couple of taps available that you could use as flush ports. So basically, there's not much going on here. There's 7 parts. Raw sewage inlets, a lot of valves on these. Sludge pumps, pretty typical. Valves 3 inch, 30 inch and over, we fabricate valve bodies. Now, what's interesting about this, if you take a look at the profile of this valve, it's eccentric. This opening inlet is eccentric to the valve body. The reason for that is we actually use the series TF1 in there. So 39Fs, fabricated bodies, 30-inch through 84-inch. All the same criteria go into the manufacture of the valve, and the same things we need to know in order to manufacture it. There's a couple of valves on their way, depending on how much space we have. Just to clear this back up again, you'll notice we don't have a lot of space for this valve at the invert, so we use a series TF1, just as if we would on an outfall valve. Where we do have space at the invert, we can create a larger valve body. We can use a TF2 on the inside. So to give you an example how this works, I'll show you this Hoboken valve. It's very hard to see, but right out here is a 72-inch Tideflex valve. This has been out there for years. So what they found in Hoboken, this goes out to the Hudson River, by the way, which is tidal. And over the years, since we installed that original valve, tides are getting a lot higher. Heavy rainfall events are occurring more frequently. Their severity is dramatic. And basically, that one line can't handle that flow anymore that it's getting. So they decided to put in this pump station, which is 72-inch, to handle excess flow. So normal flow just comes through the system, exits the Tideflex valve. At peaks and excess wet weather events, they kick in the pump station. So what this valve, how we build a 72-inch valve is, this is the base plate for the valve body upon which the Tideflex valve is mounted. This is 72-inch series TF1. That valve gets clamped on just as it would as if it were being mounted to an outfall pipe. Clamps are applied, the clamps are pinned. We want to keep that valve in place. It gets slipped into the valve body, and the result is a 72-inch ready to ship Tideflex valve. This is massive, but it's something that New York DEP is real familiar with these. They're very comfortable with them, and in a lot of cases is their check valve of choice. This is a valve that we manufactured, Waterflex valves, really to install in our Tideflex mixing systems as outlet valves. I like to show this valve here. I personally think this valve has some space industrially, replacing double discs. So the way this valve works is it's a rubber membrane held in place by a bar, mounted to a perforated plate. Again, flow, very low flow, inches of water, membrane opens. At rest, the membrane is closed, and any amount of reverse differential pressure keeps the membrane closed. I think this is something that could be developed. Right now, we're primarily using it in our own mixing systems.
Let me just give a couple comments on that. If you can go back one slide. The reason that disc is perforated, if that was open, even with 4 large pie shapes or 2 semicircle orifices on the back side, that fabric reinforced rubber would have a limited back pressure rating. That's why that perforated disc is designed that way, so it can take much higher back pressures. We even tested a 24 over 150 psi, just this Waterflex. So as Chris mentioned, it's a potential valve to use in the place of double door check valves. The face-to-face is only the flange thickness because the rod and the membrane fit down inside the pipe ID. So you'll see this when I present on Tideflex mixing systems. We use these. That's our standard outlet valve, which I'll explain. But this, like I mentioned, there's a potential for this to be used. That membrane for inline use. That membrane is not just taking a hunk of gasket and cutting a disc out of it and putting it under a membrane. That is all fabric reinforced rubber as well. You cannot use just gasket material on that. That's fabric reinforced, just like the Tideflex. The one he showed, the huge one that he showed on the previous slide, that was installed in Tampa Bay on an inlet structure to like a man-made lake that holds like 1 billion gallons of water. That valve is used on when they pull suction into the plant. When they pull raw water in, that valve closes. So that was sort of a custom design. So we've designed them as large as 84 inch. But that's the concept behind that valve.
Thanks, Mike. Couple things about back pressure. A lot of you folks are pump guys out there. One thing we need to be real careful of, I'm going to show you an application. I actually got a trip to China over this particular valve. Here's the Tideflex valve. We got a order for a couple of these, and we asked them what the back pressure was, and they gave us pipe invert to the high water level. Right, so this is the reverse differential. This is how much water the valve would have to withstand. Worst case, empty pipe. So we built the valves, we send them to them. A couple weeks later, we get the call, the valve's inverted. They literally sucked into the pipe. So I get there, I'm standing up here on this concrete slab. There's a door there. I asked them what the door was. He said, oh, that goes down to the pump. So all I did was open the door and basically walked 30 feet down into this pump chamber. So basically what happens is when the pump pumps, and this river only gets this high, it's pumping against that river level. When the pump shuts off, the column reverses, pulls a negative pressure, and now the two are cumulative. So as a goodwill gesture, we rebuilt the valves for them, took into account the negative pressure and the high water level, combined it to increase the head loss stiffness of the valve, and we're able to complete the application for them. So if you're working with pump applications, you really need to be paying attention to any kind of column reversal you might run into, because it is cumulative to that back pressure from the invert of the pipe to the high water level. And the way you can get rid of that, the easy way you can take care of that, is just use an air vac. Right, that's the simplest way. You just want to relieve the negative pressure. When that pump shuts off, the column reverses, you introduce air into the column, you break the vacuum, and you take that extra pressure off the Tideflex. This is really common. Pumps in parallel. We see this, so we have to be really careful with this. So, and I've run into this many times. So we've got 3 pumps here. They're all 3 discharge. They're all pumping 50 PSI. We asked the client, what's your discharge pressure? He goes, well, it's just discharging the atmosphere. Well, what's that mean? Well, it's just dumping out into the air. Okay, zero back pressure. Great. You build the valves, you build them to an ultralight or a light construction. Pump 1 kicks on, starts barreling out, turns the corner, slams into pump number 2 and inverts it. So years ago, what used to happen is we would put a stiffer valve in pump number 2, right? Missed check valve. Now, pump number 1 kicks on, slams into pump, whatever, number 3, kills that one too. So we are always looking at what the system back pressure is that we're trying to withstand. So it's not good enough to say discharge the atmosphere if you're working with pumped applications. You got to be very, very aware of this. So, like I said, what we're always trying to do is choose the right valve hydraulically. So we're looking at the maximum flow that we can get through the valve with the lowest head loss in order to move water for our client as fast as we can with the least penalty, head loss penalty. Now, a couple things. So as we discussed, all these valves or these curves on the chart you see are relative to stiffness. So there's going to come a point when you're going to run into a 24-inch valve. You see this high curve at 20 PSI, you're going to hit the wall. You're going to have a 24-inch valve at 30 PSI. What do we do with that? Well, we can stiffen that valve up till you won't get any flow out of it at all. Right? It's not going to do us any good. Or we have a mitigating device that we can use. We call a saddle support. So this device fits inside the Tideflex valve, It nests inside that center section of valve, if you recall, that we call a saddle, and it prevents that valve from literally caving in. What it also allows us to do is, for instance, take a 15 PSI back pressure valve, install the saddle supports, and now we can take 3 times the back pressure. So that's how we get away with that, by still providing a valve that can maximize discharge flow. Abbotsford, British Columbia, 96-inch valves. These are tough. The larger valves, generally speaking, are going to be able to take a lower back pressure. In this particular case, we needed to increase it a couple of times. Inserting the saddle supports took care of that, allowed us to complete the application. Tideflex orientations, like Mike says, bill vertical. Here you see a series TF1, mounting plate, curved bill, clevis, pin to the pipe, nice application, vertical. So what happens? Like Mike said, large diameter valves, and this can be anything into the teens. I mean, 14, 16, 18. You put them in horizontal, those things are going to, gravity's going to take over. You're not sure what's going to happen. Once flow hits them, pushes that bill down, it may not come all the way back up. I'll give you a little bit of an example of what's happening physically to the valves. That 72-inch valve we looked at before, that TF1 weighs 2,600 pounds. The weight of the water is about 7 tons. Total weight on that valve hanging off a pipe is 7.4 tons. So we got to keep that valve vertical. We can't let those things go sideways. In fact, before we had TF1s, our clients were rotating them like you see here. And what happens is that valve is okay when it's sitting there passive, but then water hits it, it pushes that valve open, and that valve may not have the energy to come back up and close again. And what you end up with is something like this. So we're very, very cognizant of installations, particularly vertical. Now, competition. So I want to move through this to give you some time to ask some questions. Proco, Onyx, EVR are generally the biggest competitors you're going to see for Tideflex valve. Clay Valve buys them from EVR. You have Rhino Valve in Australia, Blue Valve, Green Valve, Yellow Valve, Yatai Machine in China. Proco, in fact, manufactures in South Korea. So the upshot of all this is way less than 10% of the specs we see out there name one of our competitors. They're generally Tideflex specs or equal. We are the guys that, and even now, after all this time, we're spec. We're the guys that help consultants and owners determine the hydraulics of their system. What's the right valve for the job? Highest flow capacity at the lowest head loss. They're still coming to us. But the competitors bid everything, right? They're not growing the market. They're just really reducing our margins, and they're getting into our pockets. So there's not a whole lot to say about them. You can see a Tideflex TF1 and one of these manufacturers' valves sitting on the table. They're going to look about generally the same. I can assure you they're very, very different physically. The competition, we still see this. I made this list a long time ago, and it's still true now. They don't have a whole lot of experience, but they're getting there. They have limited product offerings. You know, it's an interesting thing. We do a job where we have, say, a TF1 on a mounting plate. We won't see anybody bid that. Why is anybody's guess? Anybody can build that stuff, but they don't have the comfort level for it. They have a limited product offering, especially styles, especially the amount of tooling that they have available to make valves that actually fit pipes properly. Limited or no testing. Very rarely do we see any test reports come out, any specs from competitors that cite any kind of test results. They generally don't have a whole lot of engineering support to provide to consultants and owners. as far as misrepresenting their capabilities, we've seen our own curves on their letterhead so many times, it's really not funny anymore. We are able to pretty much refute that. These guys sell at pretty low margins. They get orders. In a lot of cases, a few years later, we end up replacing those valves. So basically, their entire strategy is to chase our specs and sell on price. So they can fabricate or contract out. And generally, they make black rubber valves, and that's really their pitch. Look, this is the same as a Tideflex valve. So it's something that we see all the time. So without getting a whole lot into this, the whole idea that we try to get at all the time, because we're very specable, is to write a tight spec. You know, we ask an engineer to go in there, ask for flow data, get head loss data, get pressure ratings, reference lists. How many of these have you done? How many years have you been doing it? We ask for 15 years experience. We have consultants who are so tired of seeing competitors in there. It's 30 years experience. All of this stuff in section B, independent hydraulic testing for head loss, jet velocity characteristic through 48-inch, multiple construction stiffnesses and testing for consistency for that. That's not blowing smoke. That's stuff that we've done and we can deliver data on. Independent hydraulic testings for multiple valves at relatively the same head losses, same thing, hydraulic characteristics, finite element analysis. So we're asking the rep consultant to write a spec that makes sure that the client gets the valve that they need. So we're asking that you include the specs with your data packages and your quotes, write the right spec, review the plans and specs before the bids. That's where you're going to see things. That's where we catch things. You know, to give you an example, we get an inquiry for a 24-inch Tideflex valve. We don't see the plans, we don't see the specs. We bid a 24-inch slip-on valve. Then the plans come out, it's 24-inch concrete, should have been a 30-inch valve. So we need to be looking at those plans and specs all the time before the bid. And this way we can adjust our bids to meet the designs. Now, lastly, I'm going to show you what happens with a competitor who beats us on a project. This is Medford in England. This was a real tricky head loss issue with this outfall. So we lost this valve, and a couple things you notice right away. This isn't a full-size valve slipped on the end of the pipe. This client didn't have tooling big enough to build one valve to put on the end of the pipe. They were a little skittish about how stiff to build this valve. We'll talk about that in a minute. You see this valve's already falling off where it started to slide off the pipe. And no matter what they did, they couldn't keep that valve on there. So what they did was they came up with this chain contraption in order to keep the valve in place. Now, they built a very light valve because their expertise was not in, like Mike described, 7 or 8 different stiffnesses on a valve in order to get you the flow capacity you need and withstand the back pressure. And eventually that valve just immediately turned inside out the first time it got hit. So that's the kind of stuff we see constantly. That's the end of the presentation. Anybody have any questions? We can go from there.
Tell you what, yeah, good job, Chris. That was well done. There's some questions here in the QA session, and this is Mike Dewar talking first. First question.